In the last class, we discussed this, that we defined Laplace transform of a function as integral 0 to infinity e power minus st of that function. And that function will be in terms of the parameter s. Now, there were elementary Laplace transforms of these formulas. Laplace of 1 is 1 by s, t power n is n factorial by s power n plus 1. Laplace transform of e power a is 1 by s minus a. Then sine at cos at, then sine hyperbolic at cos hyperbolic at. These were the basic Laplace transform. Then we discussed, the linearity property, then the shifting property, the first shifting property. Yeah. That if you multiply with e power at, s gets replaced by s minus a. So all those properties we discussed, then change of scale, then second shifting property, and then we did a number of problems. Then we went into a second level of properties, that is multiplication by t power n. If function is multiplied by t power n, then the Laplace transform of that function will have to be differentiated n times with a multiplier minus 1 to the power n. So this was the proof for it. Now division by t. So multiplication by t is differentiation, division by t is integration. And then there's Laplace transform of derivatives and that of integrals. So Laplace transform of derivatives, this is a very important result. Nth derivative Laplace transform is s power n, and Laplace transform of f minus s power n minus 1, and Laplace transform of f putting s 0, then this function Laplace transform of s, this is the original function, substituted 0, then differentiated and substitute 0, then second differentiation, substitute 0. So this formula we'll have to remember. The Laplace transform of integrals is 1 by s Laplace transform of the original function. So we did a few problems on this, and that's where we stopped. So now let's consider further a few more problems. So this problem 5. Okay. So problem 6. So division by t should give us integral. So that's what we need to do. So now find the Laplace transform of 1 minus cos t upon t square. So let us do this. Now first let's do Laplace transform of 1 minus cos t. So this is Laplace transform of 1 minus Laplace transform of cos t, which is 1 upon s minus this 80. So we get s upon s square plus a square. That is the um, s square plus a square, that is 1 square. So this is Laplace transform for cos. Next, uh, now Laplace transform of 1 minus cos t upon t. Now this is integral s to infinity, integral s to infinity, f bar s ds. So this becomes integral s to infinity 1 by s minus s by s square plus 1 ds. So this is log s, and this is multiply and divide by 2. So numerator 2s will be the derivative of this denominator s square plus 1. So the integral is log of s square plus 1. Now applying the limits s to infinity. Now to do this, we'll have to use limits because log infinity is not defined. So we write it in this form. So when this s tends to infinity, log of, so there's an improper integral. So what are we left with? Upon this, as s tends to infinity, you can divide by s, numerator and denominator. We'll get 1 upon under root of 1 plus 1 by s square. As s tends to infinity, it will 1 by under root 1 plus 0. So this becomes log 1 minus log s by under root s square plus 1. Okay, so this is log of under root s square plus 1 by s. We can also write this as half log s square plus 1 minus log s. Now, Laplace transform of 1 minus cos t by t square. That is, to this transform, again, we divide by t, which means we will have to integrate this result. So now let us do an integral. This by itself, it will be a little difficult. If we do as it is, let's try. So first function is this into integral of 1 minus integral of the derivative of this. So derivative of log is 1 by log x is 1 by x. So when you do that, s by under root of s square plus 1 into Then the derivative of this portion, 1 by s into s square plus 1 into 2s, 1 by root 2. First function derivative of the second plus or minus, keeping this as it is, derivative of this one. So you get log of, we can take this inside, 1 plus s to the power minus 2 times s minus, now let us do a calculation. Ah. Oh, I'm sorry, we have to apply the limits. So we'll simplify this first. When you multiply this term, s cancels, 2 remains. We get, no, 2 cancels, s cancels. We have s over s square plus 1. And this plus, this multiplies this, and this term cancels. We get 1 by s. So applying the limit, this is infinity into log 1 0. Of course, using L'Hospital's rule and all, you can show that this is 0 minus s log of 1 plus minus 2. And then substituting infinity, this is 0 plus 0. So this is your result. This is Laplace transform of 1 minus cos t upon t square. So we have to do by integration. So we get a square minus, okay, s square minus 1 upon s into s square plus 1 minus s log of 1 plus s to the power minus 2. Okay, so this is about Laplace transform. Next, one more we'll do. Now evaluate Laplace transform of e power minus t into integral 0 to t sine t upon t dt. So now we have to use different parameters, different Now there's a Laplace transform of an integral. So first, first steps, first solution, we will start with the sine t. Laplace transform of sine t is 1 by 1 square plus s square. This is 1. What will be Laplace transform of sine t over t? So division by t means it is integral. So this is tan inverse s from s to infinity. Okay. So now tan inverse infinity is pi by 2 minus tan inverse s. So you can write this as cot inverse s also. Doesn't matter. Now I want Laplace transform of the integral 0 to t, the integral. Now Laplace transform of integral is 1 upon s and Laplace transform of the original function sin t by t. So I get 1 upon s cot inverse s. After that, Laplace transform of this now shifting property we have to use. E power t times the integral times this term. So we have to replace s by s minus a. Now a is minus 1 here. So minus of minus 1 becomes plus 1 s minus a. Now a is minus 1. So you get s plus 1 cot inverse s plus 1. So this is the solution. Okay, similarly, one more type of this integration differentiation. Now evaluate integral 0 to infinity t e power minus 3t sin t dt. Now evaluate when, sorry. So evaluate this integral by Laplace transform. That is the um, now the question is evaluate the integral by Laplace transform. Okay. So this itself is a Laplace transform. If you see this, what we can do, so we can write this integral as integral e power minus st into t sine t dt, integrating from 0 to infinity. This is the basic definition of transform of f of t, t into sine t, where you put where s is equal to 3. So evaluate the transform, Laplace transform, and substitute s equal to 3. So this t e power minus 3t sine t. This apparently is difficult integral, 0 to infinity. But you would consider this one as e power minus st. So now this is nothing but Laplace transform of t sine t. Now multiplying by t means differentiating once. So it is minus 1 to the power 1 times differentiating the Laplace transform of sine t. So we get minus d by ds of 1 by s square plus 1 square. So when we differentiate this, we get minus of minus plus 1 by s square plus 1 the whole square times 2s. So we get this as the Laplace transform. Now here we have to substitute s equal to 3. Now put, so you get 2 into 3 by 3 square, 9 plus 1, 10 whole square. So 2 into 3 by 10 square is 100. So answer is 3 upon 50. So this value of the definite integral is 3 upon 50, and we used the concept of Laplace transform to very easily do this integral. Otherwise it was going to be a very difficult integral because it's a multiple of 3 functions. Okay. All right. Let us do another one. How will you do this? Okay, evaluate. This is apparently an integral problem, but by intuition, suppose you have to evaluate a strange integral like this: sine power mt upon t. Sine t by t antiderivative does not exist, in the sense we cannot find. It is one of the indeterminate integrals, or inexplicable integral. So now this is sine mt upon t dt. What we can do is, um, we can take this as e power st and e power minus st, putting s as 0. So this integral is same as integral 0 to infinity e power minus st into sine mt upon t dt, where s equal to 0. So this is Laplace transform of sine mt by t, and then put s equal to 0. So this is integral of, when you divide by t, it is integral s to infinity Laplace transform of sine mt. Mt Laplace transform is in terms of s. So we get m square by s square plus m square ds. So we get this as m square into 1 by a. 1 by a is 1 by m tan inverse x by m x by a. So this is the integral s to infinity. So 1 by m comes out, it cancels m. Then tan infinity is pi by 2 minus tan inverse s by m. Now, we have to put s equal to 0. Now, if you put s equal to 0, m. Sorry, this is not a square, this is a only. So this m doesn't come here. Now put s equal to 0 because that's the original premise. So therefore, this integral is pi by 2 minus tan inverse 0, which is pi by 2. It is pi by 2. Okay. So this is how we use Laplace transform to find integrals also. All right. Now we move further. We have Laplace transform of some special functions. Laplace transform of some special functions. So the first type of function is unit step function. Now this is also called as the Heaviside function. This is called as the Heaviside function. So this function is defined as just hold on. So this function is defined as it's a unit step function. That means it will be 0 when t is less than a, and it will be 1 when t is greater than a, and it is undefined when t is equal to a. So the graph of this function looks like this. This is t and this is u of t minus a. So the graph will look like this. this is A, and till t is less than A, the value of the function is 0. At A, it is not defined. Just after A, the function value is constant 1. So this is called as the unit step function. So step function, which is equal to unit, and it is like a step, a jump. And this is also called as the Heaviside function. Now, very important here, A has to be non-negative constant. Where A is a non-negative constant. Now, so now let us do this Laplace transform of u of t minus a of this unit step function. So it is integral 0 to infinity e power minus st, the unit step function dt. Now, when we do this, we have to split from 0 to a integral, and this one between 0 to a, we will just do that, and we split from a to infinity. Now, between 0 to a, this term is 0 because t is less than a, so this will be 0. And between for values greater than a, because this is the limit, this is equal to 1. So this term goes to 0. Now this term is just integral of e power st. So it is integral of e power st upon minus s from a to infinity. Now s is positive quantity, we know that. So this minus 1 by s taken out. Now e to the power minus s times infinity, approaching infinity, minus e power minus s times a. Now e power minus infinity is 0 minus e power minus as. So we get e power minus as upon s. So this is a very important result. The Laplace transform of this unit step function or the Heaviside function is simply a power s minus a power e power minus as upon s. Now when a is equal to 0, this term becomes 1, so it becomes 1 by s. Now using this, we can do the second shifting theorem that we have already discussed. So these are special functions, so we will link to this. So this is the second shifting theorem. Or t shifting theorem. Now, if L, the Laplace transform of f of t is f bar of s. Then Laplace transform of f of t minus a times the unit step function. This will be e power minus as times f bar of s. Okay. Now this we need to show. So let us start. Laplace transform of f of t minus a times unit step of a is integral 0 to infinity e power minus st into f of t minus a into unit step function u of t minus a. Now we have to split into two, 0 to a. Now in between 0 to a, this term exists, this term exists, this becomes 0. And from a to infinity, this term exists, this term exists, and this term becomes 1. So this term is 0 plus this term. This is t to a. So I'll just leave it here. Now substitute, put t minus a as some y or x, doesn't matter. Dt is equal to dx, and see the limits. This is t, this is x. When t is a, x is 0. And when t is infinity, x is also infinity. So I convert this to 0 to infinity. And e power minus s into t. T is a plus x. Now this is f of x dx. Now we can write this as 0 to infinity e power minus as into e power minus sx into f of x dx. Now this is a constant, it comes out because the integration with respect to x, x is not there. So e into a power s, and this is the Laplace transform of f. This is the Laplace transform of f. So we get this is Laplace transform of f of t minus a into u of t minus a is equal to integral e power minus as into f bar of s. That's what we wanted to show. So this is a second shifting property. It's also an important property. So questions do come on this type. So let's see how we can do. So we'll use so on the unit step function, we will do some problems. Find the Laplace transform of f of t is equal to 2 0 sine t. It is 2 for t lying between 0 and pi. It is 0 for t lying between 0 and 2 pi. And this is for t greater than 2 pi, or say so. Now solution, because unit step function is involved, we can do this intelligently. So we can write this function in terms of unit step function. So f of t can be written as 2 times 2 times unit step function of t minus 0. Then, yeah, then this is 0. So when t is greater than uh, pi, when t is greater than pi, this will be 1, because for all t greater than 0, unit step function t of u of t will be 1. Now we have to get 0. So what you do, 2 into u of t minus pi till t is less than pi. This is 0. So you get only 2 times ut. Ut is 1. So this is what we get. Next, for this segment, we have this as sine t times u of t minus 2. So therefore f of t is 2 u of t minus 2 u of t minus pi plus u of t minus 2 pi sine t. So we get, therefore, Laplace transform of f is Laplace transform of 2 unit step function. And we found out for unit step function, yeah, t minus a, what is the solution? It is e power minus as by s. Okay. So this is 2 times. What is the result? E power minus as by s, t minus a. So a is 0 here. So you get e power minus 0 times s upon s. So basically it is 1 by s minus 2 e power a is pi. So e power minus pi s upon, look at the result, upon s. Now plus, this is Laplace transform of this formula, e power as into f of a. So now I will write this like this slightly. Now sine t is also sine of t minus 2 pi. Sine of 2 pi minus t will be minus sine t. Now minus of sine of t minus 2 pi will be minus of sine minus of minus sine t. So you will get the same. Now we can apply the result here. This is 2 upon s minus 2 e power minus pi s by s. Now plus the result is this one, e power minus as f bar s. So this is the solution, 2 by s minus 2 e power minus pi s by s plus e power minus 2 pi s upon s square plus 1. So this is the solution. So sometimes they give questions like this. Of course, if you want to do from basics, you can and find out, or you can use results intelligently. Of course, remembering so many results is also challenging sometimes. So of course, you should maintain a formula book for these results. We'll do further problems to get full grip of this. Now find the Laplace transform of first bit t u of t minus 1. Second one, t minus 1 the whole square into u of t minus 1. Third one, e power minus 2t into u of t minus 3. So let's take one by one. Now f of t is t into u into t minus 1. This we can write as t minus 1 plus 1 u of t minus 1. This is t minus 1 times u of t minus 1 plus u of t minus 1. So now Laplace transform of f of t is Laplace transform of t minus 1 into u of t minus 1 plus Laplace transform of u of t minus 1. So this is e power minus as times. So Laplace transform of t is 1 by 1 by s square, and Laplace transform of 1 is 1 by s. So we have to get this e power minus as f bar of s. So a is 1. So e power minus s, e power minus s times Laplace transform of t minus 1. Okay, this is the first one. And this is the Laplace transform of u of t minus 1, the unit step function. So this is Laplace transform of t. It is 1 by s square minus 1 by s plus Laplace transform is e u of t minus a is e power minus as by s. So we get e power minus a is 1 s upon s. So what happens is this term is cancelling. We are left with e power minus s upon s. Okay. All right. Now, what would you do to do the second one? Now, t minus 1 the whole square into u of t minus 1. So this is same as, okay. So this is multiplication by t. So okay, we can do this like this. Uh, this is function of t minus 1. So remember, Laplace transform of f of t minus a into u of t minus a is e power minus as f bar of s. And what is f bar of s? Whatever it is, f of t. So it's a Laplace transform of f of t. That means Laplace transform of t square, where f bar of s is Laplace transform of f of t. Now, which f of t? Not this particular f of t. So this is Laplace transform of, t square, not t minus 1. So you should remember this. So this gives, so therefore, now this is equal to e power minus 1 times s into Laplace transform of t square. And Laplace transform of t square is n factorial by n plus 1. So you get 2 e power minus s by s cube. This is the Laplace transform. Direct result. Okay, that was the unit step function. Now we will do unit impulse function. Next one is, the second part. This was totally on the unit step function and the associated property. Next, we move to the next property. Now this is Laplace transform of Dirac delta functions, or this is better called as the unit impulse function. Or this is called as the unit, the Dirac delta function. Okay. So this unit Dirac delta function, or the unit impulse function, is defined as it is defined as delta. Earlier it was t of u minus a, it is delta. Okay. Now this, it tends to infinity if t is equal to a, and it is 0 for all other values of t. And very important, integral of 0 to infinity of the Dirac delta function with respect to t is equal to 1. So how does this Dirac delta function look? It's a unit impulse function. Now Dirac delta function integrated means the area of this function is 1. And how is the function situated? How is it the Dirac delta function? This is, let's say, origin, and let's say this is a. Now for a small strip here, a to a plus k, a to a plus k, this value, so this width of this area is k. All right. This width is equal to k because this is a plus k. Now this area upon integral should be 1. Area should be 1 means this, if this is k, this has to be 1 by k. This particular length has to be 1 by k. So why? Because this will be of unit area. This is the graph of now this has to be made that as k tends to 0. So as k tends to 0, as k tends to 0, this strip becomes thinner and thinner and thinner and thinner, but height becomes longer and longer and longer, such that the product of the height and the width will always be equal to 1. Product of the height and the width is always equal to 1. That means the area of this rectangle will be 1. Now as k tends to 0, this strip becomes thinner and thinner, and this becomes longer and longer. So this is this is the concept of the direct delta function. So at a, um, the value will go to infinity, and right across a and across a, the value will be 0. So this is how a direct delta function is defined. So now, what is the result? The Laplace transform of the direct delta function. Earlier it was the unit step function. Now this is the unit impulse function, is given by e power minus as. For unit step function, it was e power minus as upon s. Now this is this one. Now, proof or validation for this, instead of memorizing, you can memorize, but how to do it? This direct delta function is, I'll call this as f of this function, f of k t minus a. All right. So this is direct delta function is limit k tends to 0 of this function, f of t minus a. So where f of k t minus a is equal to 1 upon k if t lies between a and a plus k, and this is equal to 0 otherwise. So now this is a unit function. So we can write this as 1 by k times unit step function of t minus a. Now, and then unit step function of t minus of a plus k. All right. So this Therefore, now I have to apply, I want to find this Laplace transform of direct delta function. The way I do it is I write this as limit k tending to 0 Laplace transform of this function, which is limit k tending to 0 1 upon k times Laplace transform of u of t minus a minus Laplace transform of so this is Laplace transform of, yeah, this is e power minus as by s minus e power minus a plus k times s upon s. Okay, just applying the Laplace uh, transform formula for unit step function. Instead of a, you have a plus k, so that is what is replaced now. Now as k tends to 0, what happens? So now what we do is limit k tends to 0 e power as minus as, we can take common, you get 1 minus e power minus ks upon ks. Now this limit, now this is constant because we are talking about k tending to 0. So this is limit, all right. We can do this 1 over limit k tending to 0 e power minus as into 1 by e power ks times e power ks minus 1 by ks. Now this is the standard limit, which is equal to 1. So e power minus as into e power 0 into this is the standard limit 1. So we get e power minus as. Therefore, Laplace transform of the direct delta function of t minus a is e power minus as. Okay, and last result. This is 3, this is 4. Laplace transform of periodic functions. Laplace transforms of periodic functions. So if f of t is periodic with period t, then Laplace transform of f of t is 1 by 1 minus e power minus st to integral of 0 to t e power minus s small t into f of t dt. So instead of 0 to infinity, we have replaced by 0 to t and 1 by 1 minus e power s and substitute the full t. So we'll not go into the proof for this particular one. We can do it. It's not so tricky as this one, but we can still do it. One more result, last one. Now Laplace transform of square wave function. Laplace transform now f of t is defined as k for t lying between 0 to a, and it is minus k when t lies between a and 2a, and and f of t plus 2a is equal to f of t. So this is a square wave and it is periodic with period 2. So the graph of this function will be like this. This is k, and then it is minus k. Then again it repeats this periodic function here. This is the square wave function. Now the solution for this is now Laplace transform of f of t here okay is k upon s, k upon s 1 minus e power minus as by 1 plus e power minus as. Okay, these are some important results. I'll stop here. Tomorrow's class will be on inverse transforms, and uh, along with inverse transforms, we will after completing inverse transforms, we will do how we apply this in differential equations. So I'll just show you this, just a second. Okay. All right. I will Okay, I was just checking the previous questions, gate questions on Laplace transform. I'll find out errors there. I'll Okay, I'll just collect it and give you. All right, for today we will stop here. Tomorrow's class will be on inverse Laplace transform and how we use this Laplace transform and inverse Laplace transform for finding the solving the differential equations.